Welcome to the Explainer. So today we're stepping into what I really love to call the mathematical playground. Look, if you've ever stared at calculus and thought, wow, this is literally an alien language, well, I've got a secret for you. It's actually built on a few beautifully simple rules of real numbers. These rules, they're the ultimate key to unlocking all that higher math. We're going to break them down, keep it visual, and keep it logical. Let's just dive right in. Here's our quick roadmap. We'll meet the number family, check out the mathematical playground rules, and look at the power of zero. Then we're navigating the number line, tackling the golden rules of inequalities, and finally, building our bridge to calculus, just one logical step at a time.
All right, Section 1, Meet the Number Family, from apples to infinity. You know, numbers do a whole lot more than just count physical objects, right? They tell us about temperature, money, distance, position. And to really grasp calculus, we first need to get acquainted with the different members of the real number family. Let's start with integers. These are your whole numbers, including 0, and yeah, our negative numbers. Take -3, for example. Negative numbers kind of get a bad rap sometimes, but they aren't bad at all. They literally just represent a different direction. It's like an elevator going below the ground floor. Or think about your wallet. If you have $5 and you spend 8, you're $3 short. That -3 is just telling you exactly where you stand.
Next up, we meet the rational numbers. Now, don't let the formal definition freak you out. A rational number is basically just any number that can be written as a fraction. Imagine taking a pizza and cutting it perfectly into 2 equal pieces. One piece is 1/2. Simple, right? But what's really brilliant is that even whole integers are rational. The number 5, that's just 5 divided by 1.
Okay, but what about the strange numbers that absolutely cannot be written as a simple fraction? Well, those are our irrational numbers. Look at pi. Its decimal expansion goes on forever, and it never settles into a repeating simple pattern. It's 3.14159, and it just keeps on going. So when you put the rational numbers and these infinite irrational numbers together, you get the real numbers. And that is exactly the road we're traveling on today.
Moving on to Section 2, Mathematical Playground Rules, formerly known as the field properties.
So think of a field not as, a farm, but as a playground where we can add, subtract, multiply, and divide, and the whole system just behaves nicely according to a set of specific rules. And our basic operations are incredibly flexible. Look at the associative property. When you're adding or multiplying, shifting the parentheses around doesn't change your result at all. Then there's the commutative law. Basically, order doesn't matter. 2 times 3 is exactly the same as 3 times 2. We've also got identity elements, 0 for addition and 1 for multiplication, which leave your original number completely untouched. And finally, the inverse property. This means every number has a mathematical partner that completely cancels it out, like 5 and -5, giving you 0.
Now, let's see how all this builds into one of the absolute most critical rules, the distributive law. Imagine you've got a toy box, and inside are 2 items, B and C. If you have a multiplier A sitting outside that box, it can't just multiply one item and call it a day. No way. The A has to visit both B and C. So A times the group B plus C becomes A times B plus A times C. Seriously, this little visualization is an absolute lifesaver when your equations start getting complicated.
All right, Section 3, the power of 0, the zero product rule.
0 is such a unique number. It wields this power that can be surprisingly destructive, but also incredibly handy for solving problems. The big takeaway is right here, the zero product rule. If you multiply 2 things together, let's just call them A and B, and your result is 0, well, there's absolutely no way around it. Either A is 0 or B is 0. This rule is going to be your best friend when you're solving equations. But you got to remember, 0's power has hard limits. It has no mathematical partner, no reciprocal. And that is exactly why dividing by 0 is strictly forbidden in our playground. There is literally no such number as 1 divided by 0.
On to Section 4, Navigating the Number Line. Right is bigger, left is smaller.
Okay, this is where we really set the stage for calculus by mapping out exactly where all these numbers live in space. Imagine a giant infinite straight road. This is a brilliant way to see how real numbers are organized. You've got 0 sitting right in the center. Moving to the right means the numbers are getting bigger, and moving to the left means they're getting smaller. This physical positioning tells us exactly why 3 is greater than 2, it's further to the right. And crucially, it's why -2 is actually greater than -5. Even though 5 might look like a bigger number, -2 is further to the right on our road.
While we're mapping things out, let's talk about how numbers agree or disagree when we multiply them. I like to think of it like friend groups.
If two numbers have the same sign, like they're both positive or both negative, they agree. Same friends give you a positive result. But if they have different signs, one's positive, one's negative, they disagree. Different friends equal a negative result. It's just remarkably simple logic, but it keeps our signs perfectly in order every single time.
Section 5. Golden Rules of Inequalities. The Hungry Crocodile.
Inequalities are basically the core language we use to define boundaries, limits, and restrictions on our number line. In fact, the formal definition of greater than is actually based on subtraction. To say A is greater than B really just means that A minus B results in a positive number. Like, if 5 is greater than 3, it's because 5 minus 3 is a positive 2. Makes sense, right? And hey, if you ever get turned around, just remember the classic hungry crocodile rule. The open mouth always points toward and eats the bigger number.
These inequalities also link together perfectly through what's called the transitive law. Let's look at a totally relatable example. If dad's height is greater than mom's height, and mom's height is greater than the kid's height, what do we know for absolute sure? Dad is definitely taller than the kid. You can chain these relationships endlessly, and the logic holds firm every time.
Now, here's a question that brings up probably the most frequently forgotten rule in all of algebra. Why exactly does the inequality arrow flip around when we multiply both sides by a negative number? Let's solve this little mystery visually.
And here is the brilliant why. If we start with 5 is greater than 3, and we multiply by a positive 2, we get 10 is greater than 6. The arrow stays exactly the same. But if we multiply by a negative 2, we get negative 10 and negative 6. And suddenly, negative 10 is less than negative 6. The arrow flips, because multiplying by a negative essentially reflects the numbers completely across 0 on our number line. The old right side instantly becomes the new left side, and it reverses the order of the whole shebang.
Inequalities are also great for building boxes for our numbers to live in. Look at this statement. 2 is less than or equal to x, which is strictly less than 5. What this means is x starts exactly at 2, and since it's equal to, 2 is included in the box. Then x moves to the right, cruising through 3, 4, up to 4.999, but it has to stop abruptly right before 5 because it is strictly less than 5. 5 is absolutely not allowed in this specific box.
Finally, Section 6, the bridge to calculus, your mathematical gear.
So everything we've just covered might just look like basic arithmetic, but trust me, it is your essential survival gear. If you only take away 3 foundational pillars from this explainer today, make it these. First, the number line. Positions matter. Left is smaller, right is bigger. Second, inequality logic. Saying one thing is bigger than another simply means their difference is a positive number. And third, the flip rule. Multiplying by a positive keeps your direction, but multiplying by a negative completely reverses it. These exact concepts are literally what you'll use to define rigorous limits and derivatives in calculus.
Which leaves us with a pretty fascinating thought to wrap up on. We've just seen how simple rules of grouping, order, and number lines form the very bedrock of advanced calculus. So it kind of makes you wonder, if basic arithmetic is the secret key to higher mathematics, what other simple rules out there are quietly running the universe? Keep exploring, keep questioning, and I'll see you in the next explainer.